Dear friends, this is lesson 1.1. We're doing some converting algebraic expressions into words, or expressing words in algebraic expressions, and then we're going to do some graphing of lines. So a quick recap on what you just worked on as a team. Converting words into algebraic expressions. Add 5/6 to 5 times n. So I'm adding, and I'm going to talk through what some of the little words mean just so that you can be familiar with this. Basically, anytime you get a word problem, you're going to have to translate it into numbers. You're going to have to generate algebraic expressions that match what the word problem says. Okay? So that's why I'm going to talk through this. If I'm adding something to something else, that actually means I need to start with the second part of this. I have 5 times n, and since multiplication is the default operation of algebra, I can just write 5n, and it says that to that I'm going to add 5/6. Okay? Number 2, the sum of d and 6. I need to know that sum means which operation? Addition. So I've got d and 6. I could write d plus 6 or 6 plus d. 9 is subtracted from 1/5 of m. There's a couple different ways to write this one. I'm going to start with 1/5 of m because I know that 9 is going to be subtracted from that. I could also write this one as m over 5 minus 9. This means m divided by 5. If I take m divided by 5, I'll have 1/5 of m. Okay? But right here I have default operation, multiplication, which is the of part, 1/5 of m. Take away 9. How are you doing so far? 2/3 of the sum of 4 and m. So I'm going to have 2/3 of, which means I'm going to be multiplying. But then I have the sum of 4 and m. The sum of 4 and m, the of there doesn't tell me multiplication because the word sum tells me addition. So I know I'm going to have 4 plus m. And I left myself a little gap here because I'm going to take that as a group. And I have 2/3 of that group. Okay? There's another way to write this. Because of the properties of these expressions or of the operations. But I could do this group times 2 and then divide the whole thing by 3. That would also be 2/3 of 4 plus m. Okay, as long as I have 4 plus m and then I'm multiplying it by 2 and dividing it by 3. That'll give me 2/3. And once you get to this kind of stuff, like to figure these out, you'd put in your calculator if you knew what m was. But you do need to be able to express it in these ways. 5. 2 less than 7 times k. 7 times k, and I need 2 less than that. 3 is subtracted from y. That one should have been piece of cake. We'll carry on. 7. 5 divided by n. Now this one, up here, we had a variable in the numerator and a value 5 in the denominator. But this time we're actually starting with 5 and dividing it by an unknown value, 5 over n. You might have also written this like this, but again, when we're working with algebra, it's easier to express division in fraction form. Number 8, take away 5 from b. These are too easy. r minus 3 is 3 less than r. And last one, number 10, 1/4 of n is subtracted from 9. So I got to start with 9, and I need to subtract 1/4 of n, or, like we said before, n over 4. That will result in 1/4 of n. Okay, go ahead and give yourself a smiley face or a sad face or nothing at all, and that's your grade for part 1 of this lesson. Okay, the meat of this lesson is all about graphing lines, and the unit is a linear system. So we're just going to give ourselves a definition of what a linear system is. So on the bottom of page 7 there, where you have a notes section, you can write linear system. Okay. A linear system. 2 equations that are considered at the same time. 2 equations that are considered at the same time. So probably in the past you've thought about, you've probably graphed things like somebody walking home at a certain pace, or somebody biking or something like that. Well, now you would be able to graph maybe two people walking at the same time, the same direction, those kinds of things. And if one person left before the other person, but one person was walking faster than the other person, you could see when the one catches up to the person, those kinds of things. You can see where their lines end up crossing. And that's going to be the whole point of considering two equations at the same time. Okay? We're going to write the point of intersection. Point of intersection is where the two lines meet. Point of intersection is where the two lines meet. I'm going to go ahead and underline point of intersection as kind of a new word for us. To solve, third point, to solve a linear system, comma, we must find the point of intersection. Okay, so that's the goal. Essentially, we're going to have a graph. Okay, we're going to have two lines. You can draw this as a helpful example for yourself. You're going to have two lines, maybe a line that looks like this, maybe a line that looks like this. Lines always have arrows because they go forever. And using different strategies, we're going to learn 3 basic strategies for doing this. Today we're just using graphing. You graph each line and you see on the graph where they intersect. But in the next few days we're going to learn more exact algebraic ways of doing that. But basically, if you find this point right there, you have the POI, point of intersection. Okay? And that is then the solution. Another important thing to note about this point of intersection, it indicates a place on the Cartesian plane, right? So this is our XY plane. How do we identify one point? How is a point identified on the Cartesian plane? How do I know exactly where that is? How do I name it?
You number the
coordinates. Okay, so it has 2 values. It has how far it is along the x-axis, and it has how far it is along the y-axis. So those 2 values right here, to solve, we must find the point of intersection. Point of intersection, let's say solutions can be expressed as ordered pairs. Ordered pairs is another word for coordinates. So right after that, I would just say, comma, that means x, y. 2 values, how far it goes along the x-axis in the first spot, and then a comma, and how far it goes along in the y-axis. That then is the solution. These lines cross where this x and this y are on both lines. This is the only ordered pair that will satisfy both equations. What does that mean? It's the only place on the whole grid where line 1 and line 2 both go through it. Okay? Any other place on the grid, either neither of the lines go through it or only one of them. But at this specific point of intersection, both lines go through that point. Do both lines go through this point? No. Do both lines go through this point? What about this point? What about this point? Okay? This point right here is the only place that both lines go through. Now, I used another word. I said that this ordered pair, this combination of x, y, satisfies both equations. I'm going to write that down. the solution xy. When I do that, I'm just saying this is how you express the solution. You express it as ordered pairs. There is another way, but we'll get to that later. The solution xy satisfies both equations. Okay, so in 1.0, you learned that lines can be expressed as equations, right? Y equals mx plus b is an equation. It's a line. It tells you what y is going to equal when x changes. It results in a number of ordered pairs. And if you have two lines that intersect, there's only going to be one point in the whole universe where they share a solution. And that solution will satisfy both equations. That means I could put the value of x and the value of y into the equation for number 1 and into the equation for number 2, and both of those equations would work. They would both be true statements. Okay, we'll come to that more specifically when we get to some examples. Okay, example 2, I believe it is in our book, is another situation. We get a word problem. We're going to translate those words into algebra. Then we're going to establish two equations. They're both going to be lines. We're going to draw those lines, and we're going to get the solution, whatever the problem asks us to do. So a couple of things that we're going to do. We're going to first make sure we understand the problem. We're going to choose a strategy, and then we're going to carry it out step by step. Check to see along the way that we're doing it correctly. Okay, so we have example 2 right here. We've got our friend Ian. Ian has the privilege of having his flying license. It says Ian owns a small airplane. And I'm just going to jot down some of the important information as we go along. You might want to underline important information as we go along. Ian owns a small airplane. He pays $50 an hour for flying time and $300 a month for hangar fee, for renting a hangar fee to store his airplane. Okay, that's what he does. If Ian rented the same type of airplane at the local flying club, it would cost him $100 per hour. All right, so you can kind of see that we already have two options emerging. Option 1, he owns, and option 2, he rents. Okay, I'm getting a little bit ahead of myself, but you can see how you're drawing that information out of the problem that's presented. How many, and here's the question, how many hours will Ian have to fly each month so that the cost of renting will be the same as the cost of flying his own plane? What are they really asking if we're translating this into algebra and a math problem? What does it mean if their cost is going to be the same? Refer back to your notes. What are we looking for?
The spot on the grid, the point of intersection.
We're looking for the point of intersection. We've got option 1, which we can represent as a linear equation, and we've got option 2, which we can represent as a linear equation. Now we have a linear system because we have two linear equations that we're going to consider at the same time, and if we graph them, we should be able to find a point of intersection. Okay, there's a couple of instances where you won't be able to find a point of intersection. We learn about that, I think, in the next lesson. But this one will. So we kind of have an idea of what we're doing. We've pulled out the important information. And what we really need to do next is give ourselves, what is there in algebra? What do you do with an unknown value? How do you represent an unknown value? You need a variable. Okay, so we need to introduce some variables. All right, so I'm going to say this is already done. In step 1, we're going to introduce variables. Okay, we're going to be solving for some unknown values. The unknown value is how many hours will Ian have to fly so that there's the same cost. So we have hours and cost. What letters would you like to use? Hours starts with
X.
H, and cost starts with
C.
All right, so let's do that. But there's plenty of options. You might use T for time instead of H for hours. Anyway, we're going to introduce variables by using a let statement. This is really important. We're going to let C, capital C. Usually variables are lowercase letters. Cost is traditionally capital. If you go into business or accounting or economics or something like that, the variable C, capital C, will always mean cost. It's just a standardized thing. So we're going to let C represent total cost. Now, when I get into doing my algebra and I end up with a number, how do I know I'm not talking about pennies or euros or yen or pounds? How do I know I'm talking about dollars? I need to specify that. All the problems, the stuff is given in dollars, so I need to let C represent total cost, comma, in dollars. Okay? Second variable, we said we were going to use H. Let H, and this time it's going to be lowercase. You could use T for time, but we're going to use H. Let H represent the time, comma, measured in hours. Okay, we've introduced variables. We have our basic information from the problem. Now we're going to set up two equations. We're going to set up two equations. All right, we're looking for total cost per month, right? It's a monthly cost. What can you say about this first one? Is there a set value that we know isn't going to change?
300.
300 per month, okay? So the cost, equation 1, give it a little 1 with a circle around it. The cost is going to be equal to 300. Is that it? That's the full cost for the month, or is there more? There's more.
Hours, so X or H.
Just plus the number of hours?
No.
Plus
50.
$50 per hour. Okay, so if I go 1 hour, it's $50. If I go 2 hours, it's 100. 3 hours, 150. So I'm multiplying that 50 times the number of hours. Do I know how many hours it's going to be?
No.
No, that's why I introduced a variable. Okay, so I'm going to add 50 times H. Okay, now this is not in y equals mx plus b, but we'll get to that in a little bit. My second equation is even easier. The cost for the month is going to be equal to what? $100 times H. 100H. Okay, there are my two sentences. Those are my two equations. They're my math sentences. Okay, I'm going to go ahead and convert into y equals mx plus b, because for this one, that's kind of the easiest way to graph what we have here. So what I'm going to do is I'm going to work with equation 1, okay? And because I'm working with equation 1, I'm not making a new equation. I'm just rewriting equation 1. I'm going to write equation 1 again here. I can do this as many times as I want until I get the equations to look like how I want them to look, as long as I'm not changing anything about equation 1. But right now, it's not in y equals mx plus b, it's in y equals b plus mx. How can I change it? I just got to swap those, right? Addition is commutative, so I can simply rewrite the equation 1 as 50h plus 300. And now I have a situation where, what do I know about this equation? I've got this part, which is called in y equals mx plus b. It's b, which is the y-intercept. Thank you. That should be automatic, please. And I have 50, which is m, which is slope. Okay, and 50 is the same as rise over run, 50 over 1. So I'm going to go up 50 over 1. That makes sense. Every time I go hours, I go up an hour. I'm going to go up $50. Then I'm going to go up an hour, and I'm going to go up $50. I'm going to go up an hour, and I'm going to go up $50. Make sense? But I'm going to start at a cost, a fixed cost of 300. Right off the bat, whether he flies it or not, he's paying 300 bucks. Okay? If he has a month where he doesn't even fly his plane, still going to cost him 300 bucks. In that month, renting would be cheaper. Okay? But at some point, it's going to be more cost effective to own his own plane, and that's what we're here to figure out. That's next step is solve. We're going to do solve by graphing. Okay? Solving by graphing is by far the least efficient, least effective method. Okay? After this week, you will almost never use it again in your whole life. But for now, that's what you know. That's what we're going to use. So solve by graphing. Both equations are nicely in y equals mx plus b form. You have a nice little grid, I think, painted for you there on the right-hand side. So just go ahead and draw your axes just inside. We're only working in quadrant 1. Okay, you're only able to fly a positive number of hours. Hate to break it to you, but it's impossible to fly a negative number of hours. So it's impossible. By the way, this shouldn't be x and y. It should be cost and time, which we used h. So it's impossible to go to the left on the h-axis, and it's impossible to convince the airport to pay you. They're not going to pay you. Okay, so you're never going to get a negative cost. So you can't fly negative hours, and you can't get a negative cost.
Unless they fly your plane.
Unless they fly your plane or they damage your plane, then maybe you have an argument, but it won't be directly related to hours unless you charge them the same rate that they charge you. All right, let's graph these things. I'm looking at equation 1. How am I going to graph equation 1 again?
You start at 300.
Start at the y-intercept, so I'll just help you out a little bit. You probably want to go up to about 800-ish if you're looking for things, and then you can split it up evenly. Yours will look nicer than mine. It'll be more exact. I'll give you a minute to set that up. And hours, you can go, every block can be just 1 hour. All right, I'm going to use 2 different colors. I'm going to use equation 1 here. I'm going to do in purple. So often I just like to kind of circle what I'm doing here. Equation 1 I'm going to do in purple. We're told we have a y-intercept of 300. So here's a really good connection to make, okay? Have I flown the plane at all?
Not yet, no.
No, Ian has not flown anything, and he's already paying $300. So after 0 hours, he's at $300. That tells you that this point is 0, 300, if we're talking about our XY coordinates, okay? Then what's going to happen? He's going to fly 1 hour, and it's going to go up $50. He's going to fly a second hour, it's going to go up to $100 more than he started, okay? Now, let's say he flies 8 hours, just so we can get 2 good points to draw a nice straight line. If he flies 8 hours at $50 an hour, how much money is he going to be adding to the 300 if he flies 8 hours at $50 an hour? Anyone know 8 times 50?
400.
400, okay? 8 times 5 is 4. 40. Add a 0, 400, okay? So he's going to add 400 to 300, which means he's going to be at 700. So yours will be perfect, mine will be okay. But let's say there's a next point. Grab your straight edge and draw that line. Now these lines don't go on forever. We're actually drawing what's called a ray. A ray has a starting point because, again, it wouldn't make sense to go into negative land. So this is a ray. It starts at 0 and goes one direction. Okay?
Well, isn't the one direction still the one forever?
Yep, that's what makes it a ray and not a line segment. A line segment stops on both ends. A ray has a start dot and an end arrow forever. That's a ray. It's just like a sun's ray, you could say. Comes from the sun, goes forever until it hits something. In which case it would be a segment.
Well, wouldn't it fade out after a while?
Nope. Okay, number 2. Line segment number 2, or ray number 2. it has a cost of $100 per hour. So if I fly 0 hours, how much do I spend? $0. $0 in that scenario. So this one is going to start at the origin. Okay? It's a direct correlation. It starts at the origin. And what's going to happen every hour?
Go up by 100.
It's going to go up 100. So if I want to use my full grid and I only want to draw 2 dots, after 8 hours of flying, how much would it cost me?
Lots.
800. All right. Draw a nice straight line through the origin and through that point. What are we looking for again? What's the point of drawing 2 lines?
The y-intercept.
Nope. Point of intersection. Go ahead and mark that point of intersection, dear friends. And on your graph, you should be able to see, if I draw a line, dotted line straight down, and I draw a dotted line straight across, what point is that? Yeah, my H coordinate, which in this case is my independent coordinate. So that's my X is 6. And up the vertical axis, I get to 600. Take a couple seconds to think about that. And then I'd like you to interpret that solution for me. What does that mean? Maybe we need to go back to the question. The question is, how many hours will Ian have to fly each month so that the cost of renting is the same as the cost of owning his own? So after 6 hours of flying, the cost will be the same. If Ian flies for 6 hours, comma, the cost will be the same. Okay, so we write a concluding statement as our final step. Realistically, it's not that helpful to find out where the cost is the same. What would be more helpful?
What the cost is.
Maybe what the cost is, $600 if he flies 6 hours. That's not really what he's trying to find out either. He's trying to get the cheapest deal he can, right? So it's more effective to say, if Ian flies less than 6 hours, which one will cost less? Red or purple? Red will cost less, which is renting. So if he flies less than 6 hours a month, he's going to have a better cost if he rents. If he flies more than 6 hours a month, all of a sudden that rental cost is above the purple line. That tells us purple is cheaper. So, and then it's more cost effective to own. That doesn't include other variables like taking care of your own plane or maintenance on your own plane, or maybe you just prefer having your own plane. You don't want to share someone else's plane. Okay, those factors come into play as well. But this is solving a linear system by graphing. What did we do? We took the important information out of the problem. We introduced variables. We set up 2 equations. In this time, we organized them by y equals mx plus b, but we didn't have to graph by y equals mx plus b. We could have graphed using intercepts, like we learned in the last lesson, or we could have graphed using a table of values. That's tedious. You don't want to do that if you don't have to. Okay, then we graphed them, found the point of intersection, which is the same as finding the solution, and then we wrote a concluding statement. Okay, would you agree that both lines go through this point? Are there any other points that both lines go through?
No.
No, they'd have to be curves to do that, right? They'd have to curve back on top of each other. Anyway, that won't happen in linear systems. There will only be one solution, 0 solutions, or an infinite number of solutions, which we'll get to later. All right, we're heading into example 3. It's another one where we're just going to find point of intersection. And this is a scenario where the equations aren't in y equals mx plus b, and it's a little bit more challenging to put them into y equals mx plus b, although you could. It looks like that's what we're going to do for one of the options here. So we're given 2 lines. The lines are, and again, whenever I write an equation, double check that I'm writing the same thing as your book. The first line is x minus y equals -1. We're going to call that equation 1. Then we have equation 2, which is 2x, and maybe I'll just do it off to the side here first because we're going to rearrange them. 2x minus y equals 2. Okay, so you might think, okay, I'm not really great at those other methods, but I understand slope-intercept form. I understand y equals mx plus b. So I'm just going to keep on using that as we move along. How would I convert this into y equals mx plus b?
Put the y on its own.
Yeah, before we get there, I notice right away that I have a negative y. The sign in front of a variable or a value is always attached to that variable or value. So this is not a positive y, it's a negative y. Negative y is not helpful to me. I need it to be positive. Okay, so I'm actually going to add y to both sides. Add y, and I won't do two-step. We'll just do it. We'll do it in 2 separate steps. So that leaves me with x on the left, and on the right it leaves me with y minus 1. Is that in y equals mx plus b?
No.
No, I need the y by itself, right? So what am I going to do next? Add 1 to both sides. That's going to leave me with, on the left, x plus 1, and on the right, y. Is that in y equals mx plus b? It is. Just looks a bit funky. I want to put the y on the left and the other stuff on the right. Now when I'm doing that, I don't need to add and subtract or anything. If a equals b, isn't it true that b equals a? Okay, good.
Indeed.
Let's look over at the next one. They give us a negative y as well, so we may as well use the same strategy. This time I'm going to do 2 steps in 1, okay? I'm going to do 2 steps in 1. So look at what I do. I know I'm going to be adding y to both sides.
And then subtracting.
I'm also going to be subtracting 2 from both sides, okay? Within the next month or so, I won't even be writing this middle how to do it. I'll just assume that we all understand, and I'll just write the next line, okay? But for now, we can do it this way. We've got 2x minus 2, and these y's, a negative y and a positive y, cancel out. So we've got 2x minus 2. Over here, I have 2 plus y minus 2. Well, plus 2 minus 2, that's 0. Just leaves me with y. Rearrange, y equals 2x minus 2. So from here, I'm able to graph these because I know a couple things about it, and I'll write it this time. I know the y-int, and I know the slope. Okay? So in equation 1 here, equation 1, what is the y-intercept?
1.
The y-intercept is 1. What is the slope?
No. 1.
Confirm? Disagree? Agree?
Because it's invisible.
There's an invisible 1 right here. Okay, how many x's do you have? You have 1 x. Okay, so the slope is 1, which for your help is the same as 1 over 1, rise over run. So you're going to go up 1 over 1, up 1 over 1. Okay, over here, let's get pink in the mix. Y-intercept for equation 2,
Negative 2.
-2, and the slope, 2, which is the same as 2 over 1, up 2 over 1, up 2 over 1. Just a heads up, I like the communication back and forth, but share the wealth. Yeah, step into the conversation, step out of the conversation for a few, so everyone gets a chance to think through it and be brave and call it out. So from here I can graph it. You guys have a graph there, so why don't you go ahead and graph both of those lines and see where they intersect. And I'll actually just give you a little tip. Your coordinate plane should look something like that. Okay, a little bit more space. The intersection is somewhere up here in coordinate 1, quadrant 1, sorry. Let's take a couple seconds to do that. 1, 2, 3, 4, 5. If you go up to 5 on the x-axis, that will be enough. And if you go up to Yeah, 6 on the y-axis, that will be enough. So hopefully you have enough room to do something like that. You also have a y-intercept. One of these is a y-intercept of -2, so you want to make sure you go down to at least that, or -3. And you can choose 2 colors or the same color, your choice, but go ahead and try to graph both of those lines using the y-intercept. Plot the y-intercept first, then use the slope to draw the line. Okay, I'm going to quickly graph these so we can see them. I've got equation 1, which I'm doing in purple, is x plus 1, so I have a y-intercept of +1, and then I'm going up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Okay, so, I mean, I can do that. Mine won't look super perfect, but by the time I go over 5, I should have gone up 5, so the point 5, 6 should be on that line. And then I can draw a nice straight line. It should go through there as well. Again, mine aren't perfect because I don't have the nice grid lines like you guys do. I can draw an arrow on both sides of this line because I can go into negative land here. There's no restrictions on the variables. It's not a real world situation necessarily. And then my next one in pink, equation 2, I have a y-intercept of -2. And then I have a slope of +2. So I'm going up 2 over 1. Up 2 over 1. So 2, 2 is on there. And that should be enough to draw myself a line. Something like this. It's not very good. When I draw my lines, I also want to make sure I label them. So equation 2 was y equals 2x minus 2. Equation 1 was y equals x plus 1. And I want to note my point of intersection, which turned out pretty good. What did you guys get?
3, 4.
Good. 3, 4 is the point of intersection. Okay? Now, that part is done. I've written the solution. We also want to be able to check. Okay? So now I'm giving you another tip on how to do this, another step that you can include. Check the solution in both equations. This is where we get to that point. Check the solution in both equations. This is what I am going to show you is when I'm talking about it satisfies both equations. Okay, so what that means is if I take my equation y equals x plus 1, and actually I want to go back up to my original, the one that they gave me, so that I can make sure I catch any mistakes that I made, because I might have made a mistake going from here to here, right? I want to catch that now. So what I'm going to do is I'm going to say, okay, here I have an equation, I have an equal sign. On the left side, I have x minus y. On the right side, rs, I have -1. All right? So now what I'm going to do is I'm going to take my solution. I have a value for x and a value for y. And I'm saying that that's the solution. Well, if it's the solution, then that point better be on line 1 and on line 2. If it's on those lines, it also satisfies the equation. That means that if I put a 3 in for x and a 4 in for y, this statement will still be true. How do I check that? Well, here we go. I'm going to put in a 3 for x and a 4 for y. And I'm going to see what I get. 3 take away 4 is -1. Did I get the same on the left side of the equation and the right side of the equation? Okay, if I can say that left side equals, and this is how we would do it often, left side equals right side, then I know that it satisfies that equation. I still haven't proven that it is a correct solution. I need to do the same thing for equation number 2. Left side equals 2x minus y. Right side equals 2. That comes from right up here. Left side, 2x minus 1. Right side, 2. I'm going to sub in my solution. X equals 3. Y equals 4. So I have 2 times 3, which is 6. minus 4. 6 minus 4 is 2. Did I get left side equals right side? If I get that in both equations, that means my solution satisfies both equations. That means my solution is on both lines. And the only way that's possible is if it is actually the point of intersection. Okay? If it was only on one of the lines, could it be a point of intersection? No. Okay? Could it be a point of intersection without being on both lines? No. Okay? Satisfies both equations, makes it a point of intersection. Point of intersection makes it satisfy both equations, but we want to check that we did our math right. Okay, so that's a check. Good. I'm going to do that exact same problem really, really quickly again. No, I'm not. I'm not going to do it. I'm just going to walk you through it. There's another option. We didn't need to convert these into y equals mx plus b. I could have graphed the lines in a different way. How? You have 3 strategies. Table of values. Okay, never use that. Takes too long and you'll make too many mistakes along the way. It's not worth it. Then this one, y equals mx plus b, or slope-intercept form. What was the third way that we could graph lines? From using intercepts. Okay, so what I could have done, if I just, you don't need to write this, but if it's helpful to jot something down, you could. I can take this and I can find the x int by making y 0. Okay, the x-intercept occurs where y is 0. So all I would get then is x minus 0 equals negative 1. So that gives me the x-intercept. For the y-intercept of equation 1, I set x equal to 0. That's going to give me negative y equals negative 1. Well, if negative y equals negative 1, what does y equal? Positive y equals positive 1. Okay, so look at this for a second. This is exactly what I ended up with for a purple line. My x-intercept is negative 1. It's right there. My y-intercept is positive 1. That's right there. And then you draw your line. Okay? Same thing with this one. I can look at this and I can say, in order to find my x int, I need to set y equal to 0. Okay, that's going to give me 2x equals 2. Divide both sides by 2. X equals 1. X-intercept of 1. There it is. To find my y-intercept, I'm going to set x equal to 0. That's going to leave me with negative y equals 2. If negative y equals 2, what does positive y equal? Negative 2. Okay? Multiply both sides by negative 1. Y equals negative 2. Oh, there it is. My y-intercept. You can draw your line. Okay, so that's another method to use if you're sometimes it'll be faster to go into y equals mx plus b. Sometimes you'll look at the equation and there will be like an odd number in front of the y, which means you're going to be dividing the whole rest of the equation by 3. And if you don't want to do that, then you just do intercepts. Okay? It's maybe one step longer, but you're much less likely to make a mistake. Okay, example 4, we're going to take this and put it into a real-world situation. You're trying to determine which internet supplier to go with in your area. So you have Brian and Catherine. They want to get internet access for their home. 2 companies in the area. Companies are IT Plus. Let me write example 4. Example 4. Company 1 is IT Plus. And what do? They have a flat rate of $25 a month for unlimited use. $25 a month, not dependent on how much you use. Then you have techies. Just pulling the important information out of here. These guys are $10 a month, flat rate, plus $1 per hour. Internet's not measured in hours, but they're simplifying this for us. If Brian and Catherine expect to use their internet for approximately 18 hours every month, what's better for them? So they're going to use usage, approximately 18 hours per month. Okay, just jotting down the important information as we move along. Represent each situation with an equation. We probably want to first introduce our variables. So I'm going to write that step again. By the way, when you're doing your practice problems, you don't need to write introduce variables and then introduce your variables. just introduce your variables. Okay, I'm doing this for the sake of your notes. Introduce variables. What are the variables here? What are we trying to find out? What can change? I'll give you a hint. It's the same letters as last time.
C and H.
C for cost. Let C be cost in dollars. And then this time we're actually going to use T for time. Let T be, it's more common to use T, and then just qualify that it's in hours. Let T be time in hours. Next step, set up two equations. Set up two equations. Well, let's look at IT plus. We'll call that equation 1. The cost is what? Cost equals, does it depend on usage at all?
No.
Nope, it's going to be 25 bucks a month regardless. You can, and equation 2, think it through, folks. 10 bucks a month plus $1 every hour. C equals
Oh, 10 plus 1.
10 plus 1H. Okay? How could I write that more efficiently?
We're doing T.
Oh yeah, we were using T. 10 plus 1T. How can I write this more efficiently?
10 plus 2.
Yeah, I don't need the 1 there. And I want to put the variable first. T plus 10. Okay? $1 per hour plus 10 bucks no matter what. Okay, from here you're going to take these two equations and I'm going to show you, I'm just going to plug them in into Desmos, and Desmos is going to pop out the answer for us, okay?
Silver.
You can do
Okay, ladies and gentlemen, I'm on Desmos. I've got my two equations jotted down. Desmos is really good. I can use C equals 25 and it'll know exactly what I want it to do, okay? But I'm not going to do that. I'm going to speak in Desmos language, and I'm going to use y equals 25. And I'm going to zoom out so that we can see what's going on here. And you can see the line that it drew straight across, no matter how many hours I use, okay? It's going to cost 25 bucks. Now my next one, y equals x plus 10. Okay, that's really clear as well. You can see I'm going through the y-axis at a value of 10, so even at 0 hours, it's going to cost $10. And then I'm going to add $1 every hour, and they're going to cross each other at 15 hours of usage. At 15 hours of use, they're both going to cost $25. So you can write that down as a solution. Write that down as your solution. After 15 hours, both options cost $25. That's not really what we're trying to find out. How many hours are they planning to use on average per month? 18 hours per month. So if they use 18 hours per month, which is over here somewhere, 15, 16, 17, 18, which one's going to be cheaper? The blue line, which was option 1, which was IT plus, the flat rate of $25 a month. Basically, if they're going to use more than 15 hours a month, they want to go with the unlimited flat rate. If they're going to use less than 15 hours a month, then they're going to want to go with that variable rate option, techies, $10 a month plus $1 per hour. Does that make sense? Point of intersection, 15, 25. One option is better to the left of that, and the other option is better to the right of that. That is where they cross. That is where the situation changes for Brian and Catherine. Good with that? All right, so our solution here was if Brian and Catherine are intending to use 18 hours per month, they should choose the flat rate from IT plus. And I'll even write if they intend or intend to use 18 hours per month. All right, folks, your practice problems for lesson 1.1 come from the worksheet that is included in your booklet. Worksheet and worksheet 1.1. You are responsible for completing numbers 1 through 4, number 8 through 10, and number 12. All right, that should be done or done-ish by tomorrow, and then you can come to class with questions. We can walk through some of that stuff.